This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we have discussed about solid mechanics and material subject in previous sessions. We have covered all topics. Theory part completed, and then also we have discussed about problem solving, and then question bank also some important questions we have discussed in the previous sessions. In today's session, I want to discuss about definition and terminology. Some important definitions is important in every module. Some definitions and terminology. Some terminology related to some topics are very, very important. So that in this session, so I want to discuss definition and terminology of simple stresses and strains. First, we will start from simple stresses and strains, and then we will see some other more definitions and terminology of various topics. These definitions and terminology so very important while solving problems and while deriving equations, so that every student should know about some definitions and terminology related. So the course outcome is at the end of the course, students should be able to explain the concepts of stress strain, material constitutional relationships, and strain energy induced in a linear or elastic, homogeneous, and isotropic materials subjected to forces. So already we have covered all these topics. So that now the student, after completion of this definition and terminology topic, after completion of this module, the student should be able to explain the concepts of stress strain and also some relationship between the strain energy induced in linear, elastic, homogeneous, and isotropic materials subjected to forces. See, the first we will start from stress and strain. So define stress and strain. So what do you mean by stress? What do you mean by strain? So later we will see the types of stresses and what is the relation between stress and strain. So how to write the relationship between elastic constants. So when an external force acts on a body, the body tends to undergo some deformation. So whenever the external force is acting on a body, the body tends to undergo some deformation due to this external load. And what will happen internally? That internally the molecules between the cohesion property will be developed. So the body resists this deformation. This resistance by which material of the body opposes the deformation is known as strength of material. So it can withstand that load. So that means its body opposes the deformation. So within the elastic stage, the resisting force equals applied load. This resisting force per unit area is called stress or intensity of stress. So the stress, now you can write stress is equal to, so whatever applied load, that is force per unit area, resisting force upon area. It gives stress. So direct or normal stress is calculated by using the following formula. So already you know the applied load and original cross-sectional area resisting the force. So that is called as stress. Stress is equal to load upon A. So direct or normal stress you can calculate by using this equation. Load per area. Now calculate the units. In the SI unit, the force is expressed in newtons and the area is expressed in meter square. Hence, unit of stress becomes as Newton per meter square. So, why? Because the stress is equal to load per area. So, the load is Newton per area a meter square or Newton per mm square. The area is expressed in millimeter square and millimeter square, and then mm square or unit force becomes as Newton per mm square. Now you can write in units in pascals. Pascal 1 Newton per meter square, and in centimeter square 10 to the power minus 4, 10 to the minus 6 Newton per mm square. 1 megapascal is equal to 1 Newton per mm square. So these are the very fundamental definitions of stress and the unit of stress. 1 megapascal, 1 into 10 to the power of 6 Newton per meter square is equal to 1 Newton. So convert into mm square. So 1 Newton per mm square will get. Next, define tensile stress and tensile strain. So now we have calculated, we have defined stress. Strain is how much deformed change in length upon, we have not discussed in strain. So strain is change in length by original length. So how much deformed? Change in length or diameter by original length or dia. So we will calculate the strain. Now, different tensile stress and tensile strain. So we will discuss here in this case tensile strain. So that the stress induced in body when subjected to two equivalent fulls as a result of which there is an increase in length is known as tensile stress. So the tensile stress acts normal to the area and it pulls on the area. See, whenever the component is subjected to tensile load, so load the component, so it will elongate. So this is after increased length. So original length is delta L. Original length is L. So now you can write the strain equation. Strain is equal to change in length by original length. See in this diagram figure shown clearly. So resisting force, whenever the component is subject to tensile load P, some resisting force opposes. So that is the strength of the material. Resisting force upon by cross-sectional area, it gives tensile stress, tensile load or tensile resisting force. So you can write stress is equal to load upon area. So the ratio of increase in length to the original length is known as tensile strain. So the ratio of increase in length to the original length. The original length is L. The after deformation delta DL or delta L. Here also the width, depth change B dash. So length increased and diameter decreased. So now tensile strain, you can write epsilon or E increase in length by original length. That is dl by L or delta L by L. This is the definition of tensile stress and strain. Next, what do you mean by compressive stress? So the stress induced in a body when subjected to two equal and opposite forces, because of which there is a decrease in length of the body, is known as compressive stress. So the compressive stress adds normal to the area and it pushes on the area. Is shown in this diagram. See, two equal and opposite forces are pushes because of there is a decrease in length of the body. So resistance, and then here shown the compressive stress. So here you can write the compressive stress is equal to compressive force by area. Sigma is equal to PC by area, compressive force by area. So now define the compressive stress and compressive strain. So already compressive stress we have discussed. So whenever the stress induced in a body when subjected to two equal and opposite forces, pushing forces acts, so there is a decrease in length, not increase. In tensile case, increase. So now you can write then compressive stress is given by resisting force upon area, that is load per area, the push load by area. So now the compressive strain, the ratio of decrease in length to the original length is known as compressive strain. So the ratio of decrease in length to the original length. So the original length is L and decrease in length is dl. The shortening is known as compressive strain. Next, compressive strain, write down the equation. The ratio of decrease in length to the original length is known as compressive strain. So the compressive strain, you can write decrease in length by original length, dl by L or delta L by L. Next, define shear stress and shear strain. The stress induced in a body when subjected to two equal and opposite forces which are acting tangentially across the resisting section, because of which the body tends to shear of the across the section is known as shear stress, shown in this diagram. So this the stress induced when subject to two equal and opposite forces acting tangentially, so that what will happen? This rivet shear off. So this type of stress is called as shear stress. So always the shear stress is stress, it acts tangential to the area. So it is represented by tau, shear stress, shear force by and shear area. Units are same, Newton per meter square or Newton per mm square. Now next plan, define the shear strain. Shear stress shown in this diagram. Shear resistance force upon shear area. So whenever the force is acting tangentially, so resistance force will be induced. That resistance stress is called as shear stress. So it is shear strain. It is a measure of the angle through which a body is deformed by the applied force, denoted by psi. The shear strain is represented by the angle through which the other faces have rotated. So as the bottom face of the block is fixed, the face ABCD will be distorted to ABC1D1 through an angle as a result of force P. See, the bottom one is fixed. ABCD is the previous before deformation. After deformation, ABC dash D dash. ABCD and AB C1 and D1 through an angle phi or theta as a result of force. So it means whenever tangential force acting, so the ABCD object plane, the bottom face distorted to ABC1D1. So as a result of P, force P. So that is shear stress and the deflected angle is the shear strain. So now you can write the shear strain angle transversal displacement upon distance AD. So in this previous diagram, you can see dl by h, dd1 by ad. So now define linear strain. So what is this linear strain and lateral strain? So the ratio of axial deformation of the original length of the body, known as longitudinal strain or linear strain. So when a body is subjected to an axial tensile load, there is an increase in length of the body. Already I told you in a previous case in tensile stress. What will happen here? Length will be increased. So, but at the same time, there is a decrease in other dimensions of the body. What are the other dimensions? Diameter. So, the body is having axial deformation and also deformation at right angles to the line of action of the plane load. Lateral deformation. One is linear deformation, length will be increased. In a lateral deformation, diameter decreased. Sorry, diameter. So length increased and diameter decreased. Shorten. So the ratio of axial deformation to the original length is called as linear strain. See, in this figure clearly explained. L, the previous length. After deformation, L plus delta L. So let L is the length of the body. P is the tensile force acting on the body. And delta L is increase in length of the body in the direction of P. So here diagram shown D and D minus delta D, the width also change. B minus delta B. Now lateral strain. So delta L increase in length, delta B decrease in breadth and delta D decrease in depth as shown in figure. Now the lateral strain delta B upon B original length or delta D by D. The change in diameter dia upon by original dia. Lateral strain. So the body, the other dimensions will be changed at right angles to the action of the applied load. So the Poisson's ratio, mu r 1 by m. So what is this? You know the lateral strain and linear strain. So it is defined as the ratio of lateral strain to the linear strain. 1 by r or mu is equal to epsilon t by epsilon L. So the lateral strain to the linear strain. The most common materials, the Poisson's ratio is the range 0 to 0.5. defined as the ratio of change in width for unit width of the material to the change in its length for unit length. It also defined the ratio of lateral strain to the linear strain. So now define the Book's law. And what is Book's law? So very, very important, this Book's law in simple stresses and strains. It states that the strain in a solid is proportional to the applied stress within the elastic limit of that solid. So already you know about stress strain diagram. The stress is directly proportional to strain up to elastic limit, within the elastic limit of that solid. Strain has no units as it is a ratio, and E has the same units as the stress, Newton per meter square or mm square. Already strain defined. There is no units. Change in length by original length. The length dimensions meter mm and original length also dimension meter and mm get cancelled. So that it has no units. Similarly, for elastic materials, the shear strain is found to be proportional to the applied shear stress within the elastic limit. So that is shear stress is equal to modulus of rigidity multiplied with shear strain. So here also you can write sigma is equal to E into epsilon or E multiplied with small e strain. So it states that Hooke's law holds good up to elastic limit. The stress is directly proportional to strain. See here shown, the stress is directly proportional to strain, and also you can write in terms of Young's modulus, and Young's modulus is equal to tensile stress by tensile strain or compressive stress by compressive strain. So E is equal to sigma by E. So units are stress units, Newton per meter square or Newton per mm square. Clear? So here shown some materials Young's modulus values. So these are the constant values. So while solving problems, so it will be helpful. So mild steel 200, aluminum 70, copper 100, cast iron 90, bronze 120, wood 10. So sometimes they will not give in our problem the Young's modulus value. So that you have to assume according to the given material. So if suppose the given material in a problem is mild steel, have to select, you have to assume the E value is 200 kilonewton per mm square. So like this have to assume. Next, extension or shortening of a bar. So what is this? Consider a prismatic bar length L and cross-sectional area is subjected to axial force P. So we have relation as per Hooke's law, sigma is equal to E into epsilon. Upon substitution E, epsilon and stress in the equation, you will get PL by A into delta L. So you can write this equation delta L is equal to PL by A. So stress already you know, Young's modulus P by A. Sorry, E is equal to stress by, so you know stress value, and epsilon is equal to delta L by L. So you will get PL by A into delta L, or delta L is equal to PL by AE. Next, extension or shortening of a bar, the above equation can be written as delta L is equal to PL by AE. Next one is define factor of safety. So it is defined as the ratio of ultimate tensile stress to the working or permissible stress. It may be written as ultimate strength by working stress for brittle materials and yield strength by working stress. So the factor of safety written as FOS is equal to ultimate strength by working stress or design stress. So in this, uh, for what is the importance of this factor of safety? To avoid failure. So always for safe design, you should select a good factor of safety value. So before designing a component. So ultimate strength, according to the stress strain diagram, this is a maximum strength. So that means the material can withstand this load. So beyond this ultimate strength, the component will fail. So what is this working stress? So it can withstand the maximum value, but the present the practical application you are working under stress. So always the working stress is less than the ultimate strength value. Suppose your maximum stress is 200, but working stress is 150. So this is actual design stress you are applying. So based on these values, you can calculate the factor of safety value. So in the case of brittle material ultimate strength, ductile material yield strength. Why? Because this ductile material having property, ductile property, brittle material having that ductile property, elasticity property. So ductile. So regain its not regain its original shape. It up to elastic limit it regain its original shape, but after elastic limit it undergoes into the plastic zone. So ultimate stress, what is the brittle material and ductile material? So it indicates some sign indication before failure. It does not give any signature. So suddenly it fails. Not in a plastic deformation. Next, how to write the relation between E and C. So what is E? E is the Young's modulus. C is the modulus of rigidity. And C is modulus of rigidity. L bulk modulus K. So now write down the equation. The relation between E and C. E is equal to 2C into 1 plus 1 by M. So what is M? 1 by M? That is Poisson's ratio. So relation between E and K. E is equal to 3K into 1 minus 2 mu. So next define bulk modulus. When a body is subjected to three mutually perpendicular stresses of equal intensity, so the ratio of direct stress to the corresponding volumetric strain is known as bulk modulus. It is denoted by K. So the bulk modulus K is equal to sigma by delta V by V, the ratio of direct stress to the corresponding volumetric strain. So the volumetric strain is change in volume upon original volume. This is change in volume. It is original volume. Clear? Next, relation between E, G, R, C and K. So we know that E is equal to 2G into 1 plus mu. So already we have seen here in this relation. E is equal to 2G and E is equal to 3K into 1 minus 2 mu. So what is the relation between these three? Young's modulus and modular rigidity and bulk modulus. So here only two, you know that between E and K and E and C and E and C, this you can write a C or G. Clear? So now from equation 1 you can write 1 plus mu is equal to E by 2G. The mu is equal to E by 2G minus 1. So equating this value in 1, the mu substitute in this equation, you will get the relation E between the E, G, or C and K. 3K into 3G minus E by G. See, after simplification, you will get 9 kg by G plus 3K. Nine kg by G plus 3K relation relation between E, G and K. So next, volumetric strain. Define volumetric strain. The strain in x-axis direction due to stress sigma x, that is strain is equal to stress upon E. Since the stress is equal to E into epsilon x as per Hooke's law. And similarly sigma y and sigma z. The resulting strains in the three directions may be found out by the principle of superposition by adding algebraically the strains in each direction due to each individual stress. So the volumetric strain, so write down the equations: sigma x by E minus sigma y by ME minus sigma z by ME. So 1 by M, the Poisson's ratio. So finally we will get 1 by E to sigma x minus sigma y by M minus sigma z by M. Similarly, volumetric strain in y direction strain, 1 by E sigma y inside bracket sigma y minus sigma x by M minus sigma z by M. In z direction, sigma z minus sigma x by M minus sigma y by M. So now the volumetric strain may be, you can write the equation delta V by V in terms of strain in x direction, y direction and z direction. So these are the definitions and terminology related to simple stress and strains. Next, references I have taken for these definitions and terminology. S. Ramamurtham, Strength of Material, title of the book, and publishers Dhanapati Rai. And then R.K. Rajput, author, and title of the book is Strength of Materials, and co-publishers. And R.K. Bansal, textbook of Strength of Material, and Lakshmi Publications. And R.S. Kurmian Gupta, Strength of Material, title of the book, and then publishers are Chand and Co. So these are the references I have taken for this PPT. So take any one reference for further more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.